So welcome everyone, all attendees. Here are starting the first webinar of the SLB webinar series, which will discuss the geological modeling workflow using geostatistical methods in Petrel, presented by Mr. Abdurrahman Basim from SLB. Before Mr. Abdurrahman gets started, I would like to introduce our cooperation with SLB Iraq in the webinar series, which is a series of 4 technical webinars addressing worthy themes in the oil and gas industry. We also appreciated their efforts making this collaboration comes to life. The first one is about today's webinar. The second one will be talk about technical information evaluation, will be addressing by Mr. Amin Mansour. The third one will be explore bibasin nodal analysis and VFP tables generation for reservoir engineering simulators, will be presented by Taiba Majid and Duha Arif. The fourth and the last one will be talk about OFM reservoir surveillance and forecasting, will be presented by Taiba Majid and Fatma Nazam. This is Muhammad Subhi, a volunteer officer of the SLB Irbil Section, and I will be the moderator for this webinar. Our speaker for today is Mr. Abdurrahman Basim. He has a master's degree in petroleum geology from the University of Baghdad, and he also has a bachelor degree in geology from the same university. He is a petroleum geologist with the Schlumberger or SLB 12 years long. He is proficient in surface 3D seismic acquisition and petrophysics, utilizing advanced wireline techniques. He also applies integrated solution using machine learning for reservoir analysis with expertise in production surveillance and optimized well interventions. Without further ado, I would like to thank Mr. Abdurrahman, and I would like also to welcome him. And now the mic is yours. Thanks.
Thank you, Mohammed. Hello, everyone, again. So, yes, as Mohammed say, we will start discussing today about the geostatistical modeling in Petrel. So, in terms of the audience, I'm not quite sure like the level of the audience. So I choose my presentation to be basic with touch on some of the advanced stuff. I will also, if you stay tuned until the end of the presentation, I will show you what is the latest technology that we have now, which is how to use machine learning technique for property modeling. And in order to have a flavor of comparing what is the conventional method and what is the most advanced method. So now I will start sharing my screen. I'll start sharing. Entire screen. Okay. Please tell me when you see my screen.
Yes, it's clear and steady.
Okay. So again, we start with geomodeling in Petrel. So as I said, I will start maybe with basic. Please, if you need any, maybe if you have any question, write it down. From now, you can stop me if you want, and I can clarify it for you. At the end of the presentation, we can also have a question and answer sessions if you like. And first, I would like to start by explaining like the motivation, like what is the motivation of geological modeling, why we are doing this. By understanding the motivation and where we are coming from, how we started the method, like earliest method, what was it? We will understand the new method, like we will understand the new geostatistical method. And later on, we will also discuss the machine learning. So basically, in any field, like we have wells drilled everywhere. Let me just open my laser, my pointer. Okay. So imagine if we have wells drilled everywhere. Like, I mean, in some locations in your in the field, like we know all the data coming from these wells are real data. We consider it as a real data, and we will count on it. But we want to understand and to know what is between these wells. Okay, so we want to know what is between these wells, and this is the main motivation, like why we are creating, why we want to do this model, why we want to create model, because we want to fill the spaces, we want to fill the empty spaces between the field in order to understand the environment. The moment that we understand the environment, we can track the fishes. We can track the good fishes. My pointer is a bit slower. Okay, I will not point much. We will track the good fishes, and then we, of course, we're going to drill on these good locations. We're going to make estimation of the volumes, and later on we can give this model to the reservoir modeling, and he will make simulation and make different simulation studies like injection and history matching and production, and do all his work on it. So that is our main motivation for it. So what is the model? Model is basically we are defining a space. So it is not only important for us to know the environment. We want to digitize this environment, like give value for each space in this model. So the model can be defined as a space like in X and Y and Z, which is measured in distance. For example, or we call it cell. This one we call it cell, which is maybe sometimes, for example, this cell is measured in 50 by 50 meters. And you can see here we are compromising the resolution of my reservoir by selecting bigger cell or smaller cell. All that will affect the resolution of your model. So this is another illustration about how cells look like relative to your earth. So basically, this is autocrop. This is something available on the earth. We can see it. But what we want to do is to model the reservoir that look like this underneath the earth. So this is represent the size of the cells. So you can see we can either select a very fine on the right side. We are using very fine distance and very high detail. That will give me very high detail of the reservoir, or should I call it a very high resolution. And to the left side, I have an increase in size and of the cell, which is uncompromising resolution. So what is it that we want? What is our objective? Of course, my objective is to have a very detailed picture of the reservoir. However, the size of the model will be very huge because we are trying to model entire field, and if I'm using all small cells, maybe it will take a very long time to process anything, to process volumes, and it will be even worse if you give it to the reservoir engineer. He will take maybe a very long time in order to process one simulation. So that's why we will go with we will compromise. We will say, okay, we can make, for example, if you see this layer, okay, you see my cursor, right? I don't know why it's moving very slow. Okay. Anyway, you see this layer. there is no need to make a high detail for this layer, so we can just model it with one or two cells vertically. And if you see the lower part of this outcrop, it has many layering, thin layering, so it deserves to be maybe multiple cells rather than just two cells. So we need to find a balance between making a very making a light model in terms of calculations, like optimizing the model, and in terms of having a good resolution to cover the geology. So we just need to put this in our mind. This is the one of the basic things, and we do this in the step of layering or gridding. The other thing, the model that can be also defined in time. So that is the dynamic model. So the model can be either static or dynamic. So static is the one that done by the geology, which is what we are discussing now. But then the reservoir manager will use simulation to create a different value for each cell with time. So each time change, the values in each cell will be changed. I'm talking about maybe saturation, maybe pressure. All the dynamic data will subject to change, while the static data will stay same, which is represent the static model. The objective of reservoir modeling. This is also important. Because I meet many people sometimes. Sometimes they ask me when I will explain the reservoir modeling for you. People may ask, like, they will see it is a very statistical method or statistical based method. So it is based on probability, based on we have higher probability to have good porosity, low probability to have a channel here. Like, it is based on probability and statistics. So some might say, like, what if I want to drill well here? So you need to know the objective oil model. So by having I will discuss this stochastic method later. So by having a stochastic method which is based on multiple realizations and based on, and it will give you uncertainty, you will have more understanding on a reservoir in a general way, and you will have more understanding on the uncertainty rather than just figuring out location of good porosity and bad porosity between the wells, because everything between the wells remain unknown. We are only estimating probabilities, and we will put it into uncertainty. And here come one of the most important thing, which is also, I will talk about it in maybe a couple of the slides in later, which is the uncertainty. So your objective of modeling, according to this table, depend on what stage you are. Are you in exploration or appraisal or development? So in case of exploration, you all know that we have a very less data. Usually fields with exploration stage, they have maybe 1 to 7 wells, maybe 7. Very, very low numbers of wells. If you create model out of these wells, especially, and you don't have seismic, is it applicable to go ahead with this project? Yes, it is applicable, but you are retaining a very high uncertainty. So you need to understand, as you can see, identify and quantify key uncertainties is moving with us from exploration until very high levels of development in the field. So each time you make a study, you need to estimate uncertainty, and then your plan is to reduce this uncertainty by making a plan of what the data that you need in the future, what type of data you need in order to reduce this uncertainty stage by stage. And this will come with us all the time, like with all the life of the field, we need to measure this. So again, it depends on your the reservoir modeling objective depend on the stage of the field, maybe, and the most important part is that you are measuring uncertainty at each stages and trying to reduce it with time by collecting data that will that will reduce your uncertainty. So that's in terms of objective. In terms of the workflow, this is a big picture. This is a big picture of the workflow. Generally, we start with this one. I just need to move my mouse here. We start with the structure framework. Sorry, the mouse is not moving. 1 minute. Let me just remove it. Can you see my mouse? I mean, the laser was
yes,
very
it's
fast.
moving.
Yeah, the mouse now is moving faster, right?
Yes.
Yeah. So this one is the structure. First thing in geomodeling, like in general, and maybe in any software, you need to start with structure, building structure. So structure mean maybe having seismic. If you have a seismic data, you need to pick your horizons and pick your faults. These are the main parts of building the structural framework. I mean, geophysicists are spending a very long time picking these horizons. So this is like a not easy step. This is like a whole team is working on this part only to deliver you so this is geophysics responsibilities, and then they will deliver it for you in order to create your gridding on it and make your layering and so on. So this is like many geophysicists spending long time only picking, QCing their geophysical data in order to help you to create your grid on it. So then you will have your cells, the cells that we talk about it, based on this structural model that I created before. After that, the most important step that the geology or the geomodeler spending most of his time on it is the fishes modeling. Okay, it's here, the fishes modeling. Of course, it started by having a fishes log provided by the petrophysics. So maybe it was not explained here in this figure, but but the petrophysics should provide you with the fishes log, and he done this fishes study based on, you can create fishes analysis in different way in the petrophysics. Maybe you can only create electrophishes, maybe only lithophishes, maybe rock typing integrated with core, and so on and so forth. So depend on the size of the study. Again, each study will have different levels of uncertainty, and then we need to take it with us with the model in order to find the final answer, which is the final answer, in this case the volumetrics. We will also deliver it with a certain amount of uncertainty based on the initial uncertainty calculated with the petrophysical model, with the fishes model, with the petrophysical modeling or property petrophysical modeling. Okay, so this is where we spend most of our time. After that, we will make the petrophysical property modeling. Maybe I mention, sometimes I say petrophysical model, and sometimes I mention petrophysical property modeling. This one I mean here in Petrel. When I say petrophysical model, only I mean in petrophysical model like come from the petrophysicist, like from, let's say, from Petrel, which is basically a porosity, saturation, V-shell, net gross weight. Okay. So after doing the petrophysical property modeling, it is highly recommended that this petrophysical property modeling be guided by my features. That's why I spend most of my time on working on features modeling, because it will guide my petrophysical modeling. So in a location of a good features, for example, in this part, I will expect to have a good porosity. So this petrophysical modeling, property modeling, need to be connected and communicating with it. So your features should not be much different from your petrophysical property modeling in general. So that was in like the workflow in general. This is like the big picture of any modeling, any property modeling. Of course, after that, we will make also upscale and then export it to dynamic simulation. You remember that we have talked about the size of cells vertically and horizontally, and how we need to find balance. Maybe in the first or second slide, we need to find balance between resolution and the size of the model in terms of calculation. It will take longer time or shorter time. Even that, when you reach to this stage, you will even make it a cursor. Like you will this is considered the fine model, and then you will upscale it more, because you need to make it ready for the reservoir to run calculation, more optimized and faster than this. So in terms of Petrel, like how things go in Petrel, like basically in Petrel we have the workflow start with the seismic. As I told you, many very big teams actually are working only on seismic adaptations. Their main goals is to pick horizon, pick faults, and create velocity modeling in order to to convert time to distance. These are the main objectives. Because if they provide us the time to depth, we can then use these layers and depth. The layers that they have picked, we can use it on depth. So I'm saying this so in case if somebody is in workplace or in a project, working in a project, this is how you need to divide it, the work. Like the geophysicist should do this part, and then the geologists need to go through the correlation and do, like, for example, well top and make log correlation, well top correlation. You will do some tasks similar to the petrophysicist, but inside Petrel. And then you go through creating the structure model, which is basically you are like similarly to making a grid on your horizons and on your faults. After that, after creating also zonation and layering, which is the layering here is based on, as we explained earlier, we divided our vertical parts, how many number of cells. This one, maybe each zone, you can see from this slide, like we have here big cell and we have here a very small cell, number of cells. This depends on the heterogeneity of your reservoir. Again, we need a very high resolution reservoir, but we cannot do that because it will be very heavy. So we need to compromise. Maybe if we see for example, a formation that is homogeneous, we will just assign it a very big cell. And if we see a thin layer formations, we need to make a thin number of cells. After that, we come to the important part and an important part in the modeling, which is the features modeling and the petrophysical modeling, which is now I put a blue rectangle on this, which is the main part of our discussion today. We are discussing this part of the workflow. So for you to understand where are we in this workflow, we are here. Okay, and this is the geomodeling, geomodeling responsibilities. So again, we are starting with features modeling, and we are spending most of our time here. we are spending most of our time here because we want to use the species modeling to guide my petrophysical modeling. You can see here. Let's assume this is the porosity. Let's assume this is porosity. You can see here in the species modeling we have to create channels. This is like the channel environment. The reservoir is the channel environment. So the channel is the sand, and this is like the floodplain and on the banks of the sand, which is mainly shale or mud. Okay. So you can assume that the good porosity only in the sand layers here, and you can see here this is reflected in the petrophysical modeling. You can see in the green part, this is where the channels, and the blue part is the poor porosity, which is the shale or the mud. So that's why it's important to start with species modeling and then use it as a guide. By the way, if you go to Petrel, if you just bring any number of well, like 5 number of well, we have porosity, you go directly to petrophysical model, you create the model, it will be created. It will be created. I mean, it will not tell you you are missing something. So this workflow need to be maintained by people. For the software will accept anything. You can start from here, no problem. You can start from here and you can generate a model. But your model will not reflect geology. Okay, so put this in your mind. The Petrel will not tell you geology. Petrel will only calculate for you. There is a common saying. We always mention it to the people. If you cannot draw it, you cannot model it. So even this species modeling, this is not something figured out by the software. This is something should be figured out by you or by the geology in your area or in your project. So you need to be able to have a big understanding on the geology before you come here and make the model. Because I can make the same data look like rivers, I can make the same data look like a carbonate ramp. Okay, I can make it sand river, I can make it carbonate ramp. So the Petrel only will calculate for you. You need to tell him the environment, and you need to make it look like similar to the imagination that you have in your mind, or similar to the geology or to the expert geology in your location or in your project. After finishing petrophysical modeling, then you are ready to go to volume calculation, and then after that, maybe a well design, uncertainty analysis, based on the objective that of the study you want to do. Now, as I told you, that this blue rectangle now, this blue rectangle workflow is shown in this slide, which is our again, this is our topic in this presentation. So how to start by doing this? First of all, of course you are running some data preparation. This is something important, like you are preparing the data, cleaning the data, understand the well tops, zonation, and everything. Okay, and then you start. The next step is to make a scale up well logs. So your logs here, as everybody may know, that logs is very high resolution data. We have the resolution of 0.1524 meter. So basically, you are having a data each 15 meter. Each 15 centimeter. So this is considered a very high resolution data. So if I use this one and create a very high resolution grid that match the same resolution of my well logs, you can imagine how big the size of the model. It will be very big. It will be very big, and we cannot handle it. We cannot make calculation on it. and even the reservoir model will complain about it because it's very big. We cannot finish one process maybe 4 months. So that's why we go up, we make a scale up. I will talk about scale up in the next slide. And in order to go with the modeling, we need to start with univariate and bivariate geostatistics. We need to do analysis. We need to do data analysis. This is mainly based on statistics. So basically, here you are not doing you are not doing geology. You are doing something like statistics. So you are analyzing histogram. You are analyzing proportion, probability, finding relationship for probability, creating a variogram modeling, making a data analysis for the discrete data. So all that you are doing, we all fall under what we call it data analysis step. So you cannot skip this step. This is very important. You need to do data analysis. After doing data analysis, you can go ahead and create your fishing model. After that, you need also to prepare data analysis for your continuous data analysis. I call it continuous. I mean the continuous log like porosity. When I say discrete, I mean the species. When I say discrete, so you need to do data analysis for the species because it has it has like a flag 0, 1, 2, 3, for example. It is a flag log. It is not continuous. So it has different data analysis than the continuous data analysis. After that, you make your petrophysical modeling, whether it's stochastic, whether it's deterministic. We will discuss this later as well. Also, for the advanced user, if they want to show the geology in their model, they need to do a trend modeling, this is considered advanced topic. Maybe someday we will discuss it in a different webinar. After that, you can go ahead with the volume calculation and uncertainty analysis. So this is the basic workflow between the species modeling and petrophysical modeling. Let's go now to see the scale-up well logs. And the scale-up well logs, as I mentioned, we are converting my continuous log that is high resolution to a less resolution version. If you can see my mouse, if you see these black lines, these represent the layers in your model. So if you want to upscale, you need to select your grid. So as we mentioned, at this point, when we are doing the scale up, my structure is ready. So I have a grid. Okay, I need to select my grid before going ahead and do the scale up log. So when I select my grid, the software will pick up how many number of cells you have for this formation, for that formation. It will show here. For each cell, we are taking the average of data corresponding to this that is fall under this cell. So for example, if I have this cell a 3 meter size, if I have the first cell 3 meter size, as we mentioned, the log has a data each 15 centimeter. Okay, so in a 3 meter, you can just calculate how many sample we have. We will average all this data and put it and choose one value and put it in this number here in this cell, and we will do that for all the log. So this is called the upscale. We just averaged the value that fall inside each cell. We average it into one value. Okay. In terms of species log, so this is the continuous log, and to the right side is the species log. And then here, this is the species log that come from the petrophysics, which is considered the high resolution. And this is the one that is upscaled. You can see the layers. For example, this is much easier to understand. This cell has a sound code, so it will take a sound code, okay, which is, for example, 1 or 2 or 3, depend on your data. And you can see here that this cell has mostly a shell, so it took shell. I will show next slide a more how to say, more clearer picture. Okay, so then we have moved, we have created the upscaled log. Now, in order to QC this is very important, because we have averaged my original log. I want to make sure that I don't have loss in information. I need to make sure that my upscaled log represent the same statistics of like the continuous log. So in the right side, this is the best way to make QC. On the right side, we show histogram. We can show histogram for the green is upscaled cell, the red is the well logs, and the histogram is showing this one is the frequency, like how many times we have value below 0.05, 0.01. This is like the porosity value. This is the porosity values, and it's like the bins, and these are showing how many we have data in method, for example 0.01, how many between 0.015 porosity. Okay, and then we will compare the statistics of the upscaled data compared with continuous data. This is considered a good result. This is considered a good result. We have a very good match between them, so we will go ahead. If it is not, we need to reconsider my the number of layers I have. Maybe I need to put more number of layers here. Maybe I will average layers here. Okay, so we will do that back and forth. We will change the number of layers. We go back again, check upscale, check the histogram, and then test how good the result, and then finalize it if you like it. On the right side, we have the which is more clear to understand. We have because it belongs to the species log. So species log, we have, for example, species code 0, 1, 2, 3. So we have 4 species. Or we have 1, 2, 3, and this is in this well we do have only 3 species. Maybe the 4th species will appear in different well. So you can see in the species code 0 or the species number 0, we have very close statistics between upscale and well log. So we consider this upscaled is a very good result and representative for my formation. If you have very high difference between these two, you need to understand that your upscaled data does not represent your formation. So this is very important step. I mean, you can go ahead and make models and make everything. The Petrel will not stop you. You need to stop and check every step by yourself. This is another maybe closer example. We have, again, this is a continuous log. This is a continuous log. This is a species log. Okay, and we have these are the number of cells. Okay, these are the number of cells. So when I upscale the species, in this cell, the first one, I see only yellow, only sand. So when I upscale it, I see only sand. Okay, in this cell, I see most of the part is sand, and the rest of the part is shell. So if I use a method, you can use a method, select a method. If you are using most of, the method called most of, that means inside the cell, if the most of the data is sand, you put all the cell sand, because you need to commit to have one value for each cell. So we cannot have two value for one cell. One cell have one value. So the most of it is sand. Okay, we'll take most of it is sand. This is not correct. Yes, it is not correct, but it is statistically, it is representative for our formation. Statistically, it is representative. Again, here we have mainly shale. So we got shale. We have mainly here we have mainly shale, which is the opposite part of this cell. We have mainly shale here. So if we are choosing most of, we are picking shale on the upscaled log in this cell. Okay, and of course here is sand. We got sand. And the continuous, let's see how the continuous log look like. Again, these are my cells, and this is the upscaled result. By the way, in this slide, we are showing that we are using bias by discrete log. That means we are biasing the data of the upscaled data by the feces. So you can see, but you can disregard this part, no problem. I just need you to understand how the raw porosity is getting into one value per each cell. So the black dotted line is variables that is changing for each 0.15 centimeter. We have value at each 0.15 centimeter. But then when we upscale, we make it only one value. But you can see the value, because we are choosing maybe average. It is going through all the data, which is statistically you are representative for the formation. And here, the same thing. We are picking only one value for this cell, despite we have what? We have change. The change happened here in the middle of the cell, more than the middle of the cell. But we are biased by the feces. So all the feces here sand, so it pick up only the sand data. And again here on the high part, we are taking average. Of course, there are multiple statistical way to choose the data. For example, we have the minimum, we have the maximum, we have mean, median, average, harmonic. Harmonic mean. Different type of statistics. But all in all, they are meant to select one value for each cell. So this is, in general, this is how this is the main job of upscale. So I will show some a quick simple way of the geomodeling workflow. This is a very simple of how we start, and to see, in order to tell you where the geostatistics start. I want to know in my workflow where the geostatistics start. So imagine that we have this field. This is my field. We have multiple wells. For example, here we have 4 wells. So the first step, as we mentioned, what we have done, we have a grid, the model. We have to create a grid. In Petrel, you can make a symbol grid, which is simple, just a grid, geometrical, like X and Y and K and number of cells, number of layers, and that's it. But this one also can come from the structural modeling, which is come after the big workflow from seismic, layering, picking horizon, picking faults, and then you create your structural model, which is also making a grid, but for real earth structure. But let's do it here. Is like, this is the simple part. So this is a grid. As you can see, after I grid my model, I noticed that each well fall in one cell. This cell, maybe this cell has 50 by 50 meter. So you can imagine how much we are averaging. So when data in a field is representing maybe a 50 by 50 meter area. So you can imagine how much we are upscaling. So when I say how much we are upscaling, this is my next step. Again, this is a map. And this is how the well look like after you upscale it. This is how the well look like after you upscale it, and this is a top view. So, for example, at this depth, which is maybe let's consider the top, if you have shale, all this 50 by 50 meter will be shale. All the shale will be shale. If you have sand here in this well, all this shale will be sand, and so on. Okay. Now the next step is I want to fill the empty spaces between these wells, and here come the geostatistics. Now here come the geostatistics. I put this is like the number of things that need to do. We need to do a lot of data analysis, probability, vertical proportion, the biogram analysis. I will come to that. All that we need to do it in order to create, let's say, interpolation between these points. Okay. Now, where does this come from? This is again, I back to my symbol grid. The software, how the software do it. So basically, you might hear of the search neighborhood. You as a human, you can see that okay, I have well here, I have well here, but the software doesn't know. The software is blind. So you need to define a search method, let's call it, in order to move into all your grid, search for the data, and then interpolate between them. So what is interpolation? What we are basically doing, the simplest way of interpolation is the nearest. So what does this mean? It means if you stop on this cell, you will take the value of the nearest data. So if this one is shale, this will take shale. This will take shale because it has this one near to it. If this one is sand, this one will take sand. This one will take sand. This is like the simplest method of interpolation. Of course, the search neighborhood will move to all your grid, and inside this rectangle will test where is the real data and where is the empty spaces. He will fill the empty spaces similarly with the well data next to it. And the other method of interpolation, all are based on average. So this is as simple as it is. When we are interpolating, we are basically taking averages between these. So basically, and this, I want to test this cell. What should I put in this cell? I will take the value from this one, the known, the well, and the value from this one. I take the average, I put it here. The same thing here, I put the average, I put it here. And when my rectangle move, maybe it will take the average between this point and this point, and then it will move until it finish all the grid. However, the geologists understand that it is okay. It is statistics, but this is only pure statistics, only average. But the geologists start to understand that the distance has effect. For example, the data near for this well should be similar to this well and should be different from the well that is far. So there we have people start to use the inverted distance. So what does this mean? It is also average. But it is weighted average. So each well will take weight based on how far it is from from this cell. For example, this cell that I'm pointing with my pointer, I will take the average. It will take the average of these two values, but the weight is higher on this one, so it will be more or less similar to this one. Okay, this is the method of, and the triangular, it is pretty much the same of the inverted. I will not discuss it for now because I need to draw something, but it is not important because I put this interpolation method. These are a very basic. This is like how we started doing interpolation. This is like the beginning of the interpolation, in order to understand why we come to geostatistical method. Because maybe if I directly go to geostatistics, you will not understand. But it is basically developed from these basic methods. It is average. After all, it is average. But we try to put weight. And this weight based on the distance. In geostatistical method, the weight become more advanced. The weight become depending on the variance of the data. So here we are making, and here come the virogram analysis. Okay, so this is now the definition of the geostatistics. So it is just a branch of statistics, and it has it depends on the spatial relationship between the data. So why? Because the geology believe or assume that data that are close to each other should be similar, or in other words, statistically having very low variance, and data that are far from each other, they will have a higher variance. This is as simple as it is, and based on this understanding, we will take take a weight out from this variance function and use it in calculating of the interpolation between the wells. Okay. So why we are doing geostatistics? Basically, the shortest answer is because we don't have enough data. I mean, what does the geology wish? What do we wish? We wish to have a very high detailed picture of the reservoir, but we don't have it, and we don't have the technology to show us this. You might think of the seismic. The seismic, it is the closest thing of what we wish to do, but the seismic has a very low resolution with the meters. Like when I compare it with the well logs, it is very high resolution. It is very low resolution. So it does not give me a detailed picture. It does not give me understanding of the thin layers changing in species in the micro scale. So yeah. So again, because we have less data, we need to use statistics to understand the spaces that doesn't have data. Similar to if somebody want to make survey, to test maybe for example what type of the movie they like. For example, if I tell you to run this test in Erbil and ask the people in Erbil what type of movie they like, if you go to each people, that will take you very long time. It will take very long time to go. I don't know how many million in Erbil, but it will take you very long time to go one by one, ask them what type of movie they like. But what you do, you take sample, and the people who work on statistics, they understand this very well. So they take sample, like we check with the number of youth, number of old people, number of younger generation, and compare them and see what type of movie they like, and they will make a statistic about them. And the more data they have, the more representative to the general opinion in that city. The same thing here. The same thing. We are having well. Imagine this well are your samples. So you are picking samples, and then you will have understanding of the big picture. Okay. And now we come to the data analysis. As I mentioned earlier, before going into any modeling part, we need to do data analysis. So what is the data analysis? Well, as I said, this is data analysis related to fishes. The software will calculate for you the average thickness for each fishes, and you can make a probability. I'll discuss this in the next slide. You can make a vertical proportion and the virogram, which will take I mean the geomodeler is spending a lot of time looking after these on these virogram analysis. Okay, which is very important. It will highly affect your result. And of course, declustering. Maybe I will not mention this in detail, but by declustering we mean if you have, because in some fields maybe you have many wells at one location, and the rest of the field doesn't have location. So that means you have a cluster. So statistically, these wells does not represent the whole formation. So you need to do some statistical method here called declustering in order to remove this effect from your data. Again, in the vertical proportion, this picture is taken from Petrel. So this is the property. You are analyzing a fishes. As we said, we start with the fishes. So we are doing fishes modeling. So we start with data analysis. The proportion, the vertical proportion, these are the number of cells you have, the vertical number of, or let's say the number of layers, the layering. So what the software will do for you, he will check this layer in all your model. By the way, here until now you don't have complete model. You only have well that is upscaled. So if you have upscaled 8 upscaled well, he will go to the first cell, in each well, and will measure how much percentage you have shale, how much percentage you have sand, and how much percentage you have the other fishes. What is it? Channel. Yeah, channel, levy. Anyway, this is example. It will take. It will create a proportion of these cells, and then you can model this. You can model this vertical proportion. So your model will become more biased. For in this example, your model will be more biased to give mainly shale in the lower cells, because you create a vertical proportion, so there's high probability you have shale in the lower cell, and then here you have mixed probabilities. So that's why we will have mixed realizations, which we will see later. So that's in terms of the vertical proportion. And by the way, you need to do it for each zone. So how many zones you have? Think of zone like formations, because people are isolating their zones based on formations. So for example, even maybe the formation have multiple zones. For example, if you have Mishrif A, B, C, so think of it like this. So you need to do that for each zone. And the 3D probability curve here, previously we showed the vertical proportion. Here is the probability, and the 3D probability we are trying to get to utilize maybe seismic data which is available in a 3D space, and to utilize it to help us to predict the cells between these wells. So how we do that? We try to create relationship. In this example, we are creating a relationship between acoustic impedance we are selecting the secondary attribute. This is a seismic attribute. This one is acoustic impedance. So what does the software do? It will try to find a relationship between your feces and your secondary attribute, which is the acoustic impedance. So these values are the acoustic impedance values. So then the software will create a probability curve. So what you can tell from this, for example, if I have a value of acoustic impedance more than 15442, like more than 15,000, okay, the software will plug this cell as shell, because we have 100% probability is shell. Anything that is more than 500,400, it will be this cell will be shell. So no need to make interpolation. We are sure, because we have this 3D variable. So this is very, very important. But if we have less than 700, for example, that if the cell fall in this area, because it's a seismic attribute, so we have value in each cell. It is available. So if the cell have this value, where is my mouse? Okay, if the value have this value, then it will be like probability, either channel, either sand, or either shell. Okay, so it will be a probability. Maybe, for example, 20% sand, 20% levee, 20% shell. So then this is like equal probability, or maybe some slight different probability between these four species. And here the software will choose based on simulation he will do, and then that's why we will get different realization. It could be sand, it could be shell, it could be, okay, and based and here and from there we will have the uncertainty because of this. So here we finish from the probability. After that is the virogram, which is the one I told you earlier that we are spending most of our time working on the virogram. In this virogram, we are modeling the variance of my data. We are doing that we are testing and modeling the variance in the vertical direction. We are doing it in the horizontal direction. And not only in the horizontal, we are doing it also in major and minor. I will discuss this later, and then the next slide. So this is the component of the virogram. So basically, we call this one is the lag distance. So think of it, for example, this is your point, and this is the distance that is closer to your point, and these are the distance that are far away from your point. So the points are near you, they have low variance. Points are far from you, they will have a higher variance. But then your model will start to reach to a fixed variance, and we call it SIL. Because your variable, for example, porosity, it has, after all, it will have a fixed variance. So if your data reach to this fixed variance, that means that you have reached to the SIL, and then you need to model your virogram, and then the data, the algorithm from Petrel will just use it as how to extract the weight from it and use it in the weighted average and interpolate between the wells. This picture is it is the same thing. We're still under the data analysis. So we move into virogram tab. So we talk about proportion, we talk about probability, we talk about thickness. And the virogram, we need to first choose the parameters that are defining the search of the search cone. We call it the search cone. So what does this mean? That means if you have a well here or a data point here, you want to test the relationship and the variance distance relationship between this point and the other points. Now, I agree maybe with you. This look complicated to see, but I can show you maybe a more this one, because it's 3D. This one is 3D, but I just want you to understand as a basic concept. So these are the lag distance. So basically, in the lag 1, any data in this fall and inside this distance will be test how much variance between this one and this one, and then we will plug it into the first lag. See, this one is, if you can track my mouse, I'm now moving to the data analysis here. This is the first lag. Now the second lag, also you test how much is the variance between the data inside lag 2 and your point. It will fall here, and so on and so forth, until you will get variance for all your lag distance, and then you can start matching your model. So until this, you have finished your job, and the rest will for the software. You need to match the model, your data. This is for the vertical direction. Again, you need to put it for do it again for the major and for the minor direction. Okay. Start moving. This is example of how to calculate in the vertical direction. How we are calculating variance. So basically, in lag 1, this is like the first distance. So we are trying to find the relationship between phi 2 and phi 1, and phi 3 and phi 2, and phi 4 and phi. So these are the distance number 1. Consider the distance number 1. Okay, and then we take the average and we plug it into lag 1, and then between phi 3, here, phi 3 and phi 1, phi 5 and phi 2. So we skip one distance, and this is considered lag 2, and then we skip the 3 distance, and we considered lag 4, and so on and so forth. So and this way we will plug our diagram. That was in the vertical. In the horizontal, consider this is a map. This is X and this is Y. This is the distance. This is a map. These are wells, and these wells are data. So distance number 1, lag number 1. We are testing the data. We are measuring the variance for all a pair of data that having the same distance. So for example, we have for example, let's say 5 meter. It is not true, but let's say 5 meter. So any pair of data that have distance 5 meter, we are measuring variance. How much is the variance? We take the average of all these 5 meters and we plug it here. Next one, for the 10 meter, we will measure variance between any pair of data that are separated by 10 meter. So we will go through all the data and test how many pairs that have 10 meter distance between them, and test the variance, and we plug it here. As you can see, the variance increased because the 5 is closer to my point, so they are more similar. Here is more different. We are getting more variance. Again, for if we will test the next lag distance. The next lag distance is maybe a 20 meter. So any pair of data that have lag distance 20 meter, we are measuring variance, and then we are plug it in distance 3. After that, same thing, distance 4, distance 5, and until and so on and so forth. You will notice after a certain amount of point, you will reach to a fixed variance. What does that mean? That means these 2 points are not related to each other. They have a very fixed variance. The more that you go, a higher distance, higher lag distance, the same is the variance. That means These points are not related to each other. They are different species, maybe. Okay. And after that, after my points are fall into my diagram, I need to select the function that will fit my data. You can choose one of the three: spherical, exponential, Gaussian. It has a very slight difference. For example, I think the Gaussian will start how to say, less variance for a distance and then will go up. The spherical will go gradually up, and the exponential will go maybe very less variance and go like directly up. And this one is after you create this model, you select the function. You can, from this red dot, you can just adjust the fit. You can just fit it. After that, the software will deal with your data and will create the interpolation for you. Yeah, I was trying to explain this. Yes, we have a good picture for it. So this one is Gaussian, this one is spherical, and this one. You need to select one of these three to fit your model. Now, one of the pitfall, or one of the trap that geology may fall, is that if you have a trend in your data. So trend means if you have a log like this, if you can see my mouse, you see my data is ranging up and down, up and down, up and down, moving high and low, high and low. But in general, there is a trend of increasing. There is a trend of increasing. How this is going to appear here? It will appear like this. So what do we miss here? We miss the cell. We don't have cell now. We don't have a place where all the data converge to a fixed variance moving with the cell. We are still having an increased variance because these data in the lower part having are different and having a variance from this data fixed, which is increasing. So that's why we have this one. If you have a data like this, you need to remove the trend from the data. We can do this step in the data analysis. Maybe we can show it. I don't have a slide for this, but we can show it maybe in the future chances in different webinars when we discuss about trend and 3D trends and how to remove a trend. Because here in the virogram, I want you to remember, the virogram does not intend to model the trend of your geology. The only job of the virogram is to find the variance between the data independent from the trend of the geology. So here is the geology increasing with depth. This is called the trend. If for example, when I say that the porosity is increasing to the north, this is a trend. So we need to remove the trend. There is a statistical. There is a way. You just only match. All what you have to do is to match a curve here, and the software will understand this is a trend, and then will remove it from your data to back to the cell. Okay, because if we want to picture geology, we will use different data, different type of data. We will use a seismic, for example, in order to picture geology. But for the virogram, we are only measuring the variance. Again, this is like a picture from the Petrel showing you the virogram analysis. In this part, we are having, for example, vertical, major, minor. We need to do this for the vertical. So this is the search cone that I showed for you. This is the bandwidth. Like if I change the bandwidth, this width is an increase. And this is the angle, the azimuth. Like you want to move it left or right based on the azimuth. The search radius. This is the search radius. Because it is vertical, it is not really matter the smooth and the search radius, because it's vertical. If it has deviation, then we will need to adjust to it. So this will search the data inside the cone, and we will have lag of distance, number of lags, and these are the number of lags. Okay. After that, after you model, you will have the range, how much is the major range. The range is where we reach to the cell. When we reach to the cell, this is the range. So we have the major, the minor, and the vertical range. This is also another picture to compare between the major direction, like how to appear here, and this is the vertical. So you see here is a very high detail lines. So this is like the feces log appear to you. This is like sand, shale, sand, and this is your cone, search cone. You have to make sure that your search cone is covering all your formation. If you are doing formation by formation, not for all the data. So, for example, my formation start to here and to here. And now we are doing the biogram analysis based on this search cone. And this is the search cone in case of what? Of the horizontal, both major and minor. I will tell you now why we have major and minor. These are the wells, because it's horizontal. That means we have a map. So these are the number of wells, and these are the lag distance. These are the lag, and we are now measuring lag number one. How if for each two data that have the same distance as I explained previously, and so on and so forth. Then we will get the biogram analysis for the major and minor, and find the biogram parameter, which is the range. This is the most important part, to find the range, which is how much is the distance that we reach to the cell. That's why we need to remove the trend in case if you did not see a cell. Okay. And let me, maybe I did not have picture for this, but let me explain for you the, maybe let me have, did I have picture for this one? Okay, nested diagram is a bit advanced. I will skip it. But now for the range, and this slide show you where we can do biogram analysis in Petrel. So we can do it in biogram tab. So if you have data, just right click, go to setting, and then go to biogram. You can do you can run analysis for your biogram. Of course, you can also do it in the data analysis, which is part of the workflow of the property modeling. You can also do it inside property modeling. Like if you open the property modeling for features or petrophysical, there is a tab called biogram. So why we have to? Because you either want to do it here, which is very simple. You can just select the direction of the minor and major, and then you go ahead, or you can make high detail one. If you want to make high detail one, you go to data analysis, and when you go to property modeling, you need to click on this button here. So you will import the data from data analysis. Let me show you. I will try to open a paint here just to quickly. Am I passing my time, or is it okay to continue, Mohammed?
No, it's completely fine.
Okay. And this is I just want to quickly show you. You know the field. In the field, for example, you have anticline like this. Okay. Anticline like this. So, and this is, for example, your this is like a data. Let's say this is a feces or something. So by this I mean now the direction, for example, up is north, this is north. Let me just draw an arrow. The north direction is this way. Now what you see here, I can see my species. Let me choose color black, my species is changing quickly in this direction. Okay, for example, maybe I walk here in this direction, I walk only 200 meters and I change from shale to sand. But in this direction, I walk maybe 1,000 meters in order to change from shale to sand. So this is called the major direction, and this is the minor direction. That means you need to create variance, variogram analysis for the major and for the minor. That's why we have two variogram analysis. Three. One for the vertical, which is understood, one for the minor, and one for the major. So this is we need to study variance in this direction. We need to study variance in this direction. Okay, and we need to study variance in a vertical direction. So we need to do it 3 times. Not only that, we need to do it 3 times, and we need to do it per zone, per species. So this is a lot of work. So you need to do it here per zone. So for each zone, for each species, you need to have a major, minor, and the azimuth. Adjust the azimuth of the direction. Okay, so this is a lot of work. So each time, then you change the species and you do the same. You change the species, you do the same, and then you change the formation. You do the same for all the species. So per zone, per species, and if you have regions in your model, so it will also be per region. So this is a lot of work. So that's why some geo modelers are spending a lot of time here, and it is very easy to fall in mistakes, and it is very easy to shift to throw your model away. It was very easy to make mistake with this one. You need to be careful with this. Now we need to go the types of. So until now I have explained like the data analysis part. Now in terms of species modeling, after you finish the data analysis, you need to select the method of species modeling. So my data analysis is ready. Now I want to select what are the type of modeling we have in Petrel. We have the estimation, which is indicator, which is rigging. If you see rigging, it is variogram based, so it requires a variogram analysis. Assigned value, it is very simple. Like you make a model and you give it one value. Maybe you need this for to apply a fixed value or for your model or something. Interactive, you can Petrel allow you to create model by simply drawing, like paint. Neural network, which is artificial intelligence. All that is called deterministic. All that called deterministic. So what is the other type? You can select either deterministic or stochastic. By deterministic, all what we explain, we are doing it. We are selecting a rigging, and we are doing it once. Okay, so we will have one value. So basically, it will run analysis between them, and then we'll find the data between them. It will make interpolation. What about the stochastic or the simulation? In the stochastic, we have multiple realizations. These realization doesn't look similar, but they are similar. They have the same statistics. We will call it equiprobable realization. And you can select how many realization you want. And from that different realizations, you will have the uncertainty. Why we have that? Look at this. This is figure to the right. This give you another. How to say, another simple illustration about difference between deterministic and stochastic. So the blue point is your well. Just imagine these are your well, and you can see the interpolation result between these 2 points is like this. The blue line This is the result. This is deterministic. We apply variogram analysis and we got this result. But the stochastic, we have different realization, because maybe the result look like this, maybe the result look like this, because we don't have data here. We have only probabilities, and these probabilities could be changed. So that's why we have different realizations. Let me quickly show you again in Paint how the software do it. How the software do it. The software do it like this. For example, deterministic. First, I will explain deterministic. Let me put a bigger. So if you have point here, 1, 2, the blue points are real world data. Okay. I will not draw a grid or draw. I want to imagine this, that we have a grid, search neighborhood, data analysis, all that we have done it, and then we got the red point here. This is answer. So the software is using the blue line, the blue data to get the empty spaces, which is the red data. And we got one here, and we got one here, and we are only using blue. We are only using blue data. Okay, this is deterministic. In stochastic, I will go to the bottom part. The bottom part is the stochastic. We have world data like this. The blue points are world data. If we find interpolation between these two, we will use all the blue line to find the empty space, which is now is red. Then now this is the first one we start here. Then we will use the blue, all the blue and the red one to find another one, another red one. Then we will find all the blue that we have plus the new red to find another one. And then we will use all the blue here and the new red points to find another red one. So that's why we call it simulation, because we are simulating the data that we calculated. We are using it as real data. It is not real data. That's why we call it simulation. It is not like the reservoir simulation. It is like a stochastic simulation. We call it simulation. That means we are using a calculated data, but we are using it to calculate a new data. So that is the main difference between stochastic and deterministic. So why we have multiple realization? Because this time we started from here. If we start from I will delete this one. This time we started from here, but the software can start from different point. Maybe the software want to start from here. Wait. So brush. As you remember, I started from here the last time. Maybe I want to start from here. Find the result between here, and I got it. And then use all the new data to calculate another one. Use all the new data to calculate another one here. So you can see I have now different route of finding results. So different route of finding result will cause change in result, not change, different realizations. But because we are using the same data, we will have the same probability and the same statistics. So that's why we call it equiprobable multiple realizations. So this is the main difference between deterministic and stochastic. Put in your mind the standard work. What we do is we are doing the stochastic, because this one will give you idea about the uncertainty of your model. Because as I mentioned that we have different probability for different fishes, or different probability for different continuous probability value. So we need to understand the uncertainty, and just think of it like this: if we have all the realizations looking the same, that means the data, your data and your result is low uncertainty. If there is big difference, that means your data has a very high uncertainty. And these are the stochastic method. So the previous slide, I show you that similar to this, I show you the deterministic, which was Kriging. Now the stochastic. The main one and the standard and the most one is used is called the sequential indicator simulation. We call it sequential because of what I draw for you, because of what I draw. We are moving point by point. First this one, and then this one, and then this one. This is sequential. We are doing it one by one. And any new data we calculate, we are using it to calculate the new one. The next one, sorry. But in the deterministic, we are only using the well data. That's it. So this one is, as I told you, is the standard one, is the one that we are using. We have other modified methods, which is just in case you have environments similar to this one, like if your species is maybe the red in the middle, then the surrounded by the yellow, surrounded by the blue. If you have environment like this, you can go with the truncated. If you have environment similar to the carbonate ramp and beach environment, which is changing like this, so you go with the truncated Gaussian simulation. All these methods are using biogram, by the way. So you need to do data analysis, and then you select your method that is best match your how to say, your environment. Multi-point feature simulation. This is a very this is advanced way. We can maybe discuss it in different webinar. This is advanced. And then the object modeling. And this one, basically, you are identifying your environment as a channel, and you are telling your software to draw a channel for you. So this is something you are telling to the software to do, and you need to define the meandering size, the wavelength of the channel, the width of the channel. That's why we need the thickness of the sand. That's why we need the thickness from the data analysis. Okay, and you need to define it for the software, and he will draw for you channels. And based on the proportions of your data, he will create how many channels. He will keep filling channels until he meet the statistical number of your proportion between, for example, sand and shell. For example, you have 20% shell and 80% sand, so he will keep filling channel until he will reach 80% sand. So that's why data analysis is important. Okay, I think here is the continuous technique. It is not that big difference. We're also using Kriging, either Kriging as a deterministic or stochastic, which is multiple equally probable outputs. It will be like this. Okay. This is a summary. This is a summary of the workflow. As we say, we have a vertical proportion. We have a probability curve in order to fill the spaces that doesn't have data, and then we do a biogram analysis, and then we have the probability maps, which is something we did not discuss it in this presentation. It is an advanced topic, which is a trend. We use a trend to force my interpolation to follow the trend, whether you have a channel or something. And the trend is coming from, like if I want to give you a summary, the trend is coming from the seismic data, because seismic data is very low resolution, so we cannot use it effectively. But we can use it as a probability. We convert it to a probability and use it as a trend. It will affect your data and force your data to follow the trend like this. And then you finish the fishes model. After that, you use this fishes model to govern your petrophysical model. Now, for the uncertainty analysis, why uncertainty analysis is important? Because when we want to deliver a volumetric data, for example, how many barrels does your how many standard barrel does your reservoir have? You cannot give just one value. If you give one value, there is a high uncertainty, because all the talk that we discuss, because we are doing things all based on statistics. The real data is very less, and we are using the statistics to find the data between these two wells. So we have uncertainty, so we need to calculate it. After calculating uncertainty, we can we can measure how much each variable affecting my final output, which is the volumes. So, for example, if I have area of closure, which is the bottom the closure of the structure, maybe there is uncertainty. Maybe there is a plus minus 5 meters. It's true that you can pick it up in the seismic, but as we say, the seismic has a very low resolution, so you may have uncertainty, maybe plus minus 10 meter. How much is affecting your final result? So the software will calculate the both end, the minimum and maximum, and then will give you the difference. Like it has this much difference. So by having this, what we call it a tornado chart, you will understand which variable has the highest effect on your final result, and based on that, you will design your next step and you will design your next study. You will tell the people, okay, I need more detail about area of closure. I need to do a very detailed study about this because I want to reduce the uncertainty. And the same thing for the porosity, the same thing. And you can start by this from top to bottom in order to reduce the uncertainty, as we talked about in the beginning of the presentation. And here is the example, like for example, you have the gross rock volume. We have high uncertainty. If you have high uncertainty, how much impact you have on, for example, on your volumetrics? You have a very high impact. So that means we need to do something about it. We need to do seismic. Maybe we need to do more wells. Okay, so based on the uncertainty, we will design our next step. We will design our next plan for development plan or study, my study, where I want to focus more. All that based on uncertainty. So plus, we have seen how much uncertainty we have only in the steps of the modeling. We did not discuss uncertainty in the porosity, that come maybe in the saturation calculation and other things. We have seen how much uncertainty we have in the virogram analysis, in the proportions, in the comparing between or finding the relationship between acoustic impedance and my relationship. We saw that we have a probability, different probabilities. Maybe it is sand, maybe it is shale, maybe it is in the low part of the acoustic impedance, and the higher part we have a high certain it is shale. So all that will endure uncertainty, which need to be studied and need to be quantified in order to plan our next step. Now I have finished the part of geostatistic. I have another, let's say, a couple of maybe a couple of or 3 more slides and finish my presentation. I want to tell you about the latest technology we have. It is only since 2 years ago. It was started 2 years ago. It is very new. Now it was only available in the cloud, which in the Delphi, which is Schlumberger cloud, but now it is available in Petrel on-prem, which is Petrel in the normal PC. So this is the latest technology. We call it Ember. We call it Ember. It is basically a machine learning based method that will basically bypass all the data analysis part that we have discussed. You remember how much we talk about data analysis, how much we discuss biogram, proportions, trends. Even the trend, I did not discuss it because of the time. It requires a special webinar for only trend modeling. Even the trend, we don't need to do it here. All that will be automated inside this. So all the Ember workflow, basically, only, you see this window? Only this window. It is very simple. You put target here, you put name, you put the target, what you want to model. You want to model porosity. Okay, put the upscaled. Okay, you need upscaled. And put training features, which is seismic data. I will discuss the input in the next slide. And that's it. You click run, you have your model. You see how simple it is. It's very easy to master. And it will help you to concentrate on geology. Because in the previous part of my slides, I did not talk much geology, right? I was discussing mainly statistics. Despite I'm a geology, I'm spending a lot of time on statistics. So maybe I need to take a degree in statistics better than degree in geology in order to do that successfully. And geology will fall in mistake with the statistics because maybe sometimes he don't understand it very well. So with Ember, you don't need to go through statistics. All you need to do is to put your input. You have to make sure that your input has a relationship with your porosity, and that's it. You click run and you got your model. So what is the input? As I said, you need upscaled data. This is the only thing that you need to do from the previous workflow. And you choose any 3D variable. It could be seismic attribute. It could be geometrical attribute, inversion, seismic inversion, anything. You just create multiple attributes and you input it all here as a training. You will get what? You will get how to say? You will get uncertainty. So even you don't need to go through. I did not discuss uncertainty for workflow for you. I just give you identification about uncertainty, but you need to, after finish volumetric, you need to go to do an uncertainty workflow. But here you don't need to do it. You will have the mean because you have a variance in your data or different probabilities. So all these probabilities, you will have a mean for it. And you will have uncertainty, how much places are certain, how much places are not certain. And you have the P30, P90 based on what you want, or you can choose whatever you want. Whatever you want, like the probability that is lower than 40, maybe the probability higher than 50, depend on you. So this is estimation workflows. We still have the same idea here. We have also stimulation and simulation. Simulation, I mean stochastic. Okay, so multiple realization. Multiple equal probable realization. So this is the very simple workflow. You see that you will get separate probabilities, mean, median, all that in one click. So by comparing between machine learning probability modeling and geostatistical probability modeling, the one that we spend most of our presentation part discussing, we are discussing this part. So we talked about log upscale with a secondary data, which is acoustic impedance. We need to do QC for upscale. I mean, all that, okay, all that is the same in the both sides because we need upscale. This is the time. This is how much time it took. How much time it took for each step. Okay, they have done a study to compare between these two workflows. Now, in the data transformation, you don't need to do anything. Data analysis, data detrend. You remember I told you if you have a trend in your data, you need to remove it. You don't need to do that in the machine learning property modeling. Biogram analysis. As I told you, we spend most of our time doing this because we are doing it for vertical, major, minor, per species, per zone, per region. You don't need to do it here. Okay, zero time taken. Select data and run. I think this one is even over exaggerating. Select. You can easily, you have the data in your input. You can just drop it and that's it. So this time is over. Maybe they mean by data preparation because you need to prepare data for inversion and seismic attribute. Okay. And then you need to do features conditioning. parameter set, as I said, we need to make first the fishes modeling, then the petrophysical modeling. But here you don't need to do it. After that, you will do QC, which is for both part. For the blind test QC, I agree we can do it in both sides. Maybe they did not put it here, but we can do it for. And all that, as I said, per zone, per region, per fishes. So we have optimized 75% of workflow. Okay, and it's very easy to master. I just explained for you in this slide. Where is it? It has only one window. Only one window. You put target window trainings and run. That's it. You finish. And then you will focus on geology. Maybe you want to test different attribute. Maybe you want to test different parameter. So you spend all your time studying, not spending your time doing geostatistics. So as we said, this is another illustration that told you the data input is upscale and seismic attribute, any seismic attribute you want. It should be have a relationship with your target. Also, the algorithm will give you at the end of the result will give you summary, and which it will tell you which attribute has the major effect on your model. So if you see, for example, the stratigraphic depth has very low effect on your model, on your data, you can just remove it and put another attribute, maybe have a good effect on your data. As we said in the output, because I mean there are more details, but I don't want to go to this detail. This is maybe introduction. Maybe in the future opportunities we can make a dedicated presentation only for machine learning and the workflow. I will maybe show a demo in order to show you why we have multiple data, because for each cell we will have a distribution of data. We will have a distribution of the results, and because of that we will get mean, P10, P90, P70, P30, based on whatever you want, and you will have a certainty how much uncertain you are in some location based comparing with other locations. So I come to end of my this is how much I want to show you today. So I hope it was clear. If you have any question, anything that you want to repeat, please tell me. I know I went through the slide. I did not stop to ask you for a question, but if you have anything that you want to repeat, any question, anything that is not clear, please tell me. This is open session now for question and answer.
Asir Place said, can you give example how facies model effect on petrophysical model?
Give example. Give example on yes. Give example. Yes. Maybe the example maybe will take time, but I can maybe show you. Oh, let me see. For example, you see. I did not share my screen. Let me share my screen. Sorry, I stopped sharing. So I will repeat the question. You want to see the effect of the fishes modeling on your on the petrophysical modeling, right? Is this a question?
Could you confirm, Asir?
The effect of fishes on the petrophysical. You want to see example. It may take longer time to open Petrel and show examples. So I want to show example from my slide. You can see my screen, Mohammed.
Yes.
Yeah. In general, if you don't have fishes govern your fishes analysis, govern your petrophysical model, the petrophysical model will look more or less something like this. So you have data everywhere, and The connectivity between data depend on the range of your diagram. So if you have higher range, you will more likely see the one to the right. What does it mean? It means that the data is related to each other for larger distance. We call see, so they are connected. If you have a smaller range, the data will appear like this. If you have now, can you guess from this? Can you guess from this where is the direction of the major and where is the direction of minor? I will tell you. You can see the data is connected in this direction. That means this is the major and this is the minor. It is not connected from this side. So this is how it looks like. So that means my data is mainly dependent on the diagram. If you change the direction of the diagram, the change of all these will change like this. If you change it east-west, it will be east-west like this. Okay. And how does it look like if it was governed by it will be like something like this. I know this is species model, but let me show you a better example. So it will more or less follow your fishes. The porosity will follow your fishes. Okay. I think I have one here. Like this one. If your fishes look like this, your petrophysical model will look like this. It will follow. You can see the green. The green is the good porosity part, all following on the channel side, on the channel part. All the channels are sand, so the sand is the good part. So it will be similar like this. While without fishes, it will be something like this. Depend on the diagram mainly. Depend on the diagram like this. Okay, it will look like this. And maybe your fishes is like this. Okay, so maybe it depends on how it looks like. Maybe your fishes look like this. Scattered fishes are scattered away. So your petrophysical will look like scattered away. Okay. Does this answer your question here? Let me see. I think I have. Let's first see if this does this answer your question. I will go to the next one.
I think he left the meeting.
Okay. Now for the next question, how to determine the number and distance of whales with machine learning? Oh, okay. This is good. This is a good question. The number and distance. Well, for the distance, I mean, there is no. I mean, what is the distance of the whale? You can just all the whales in your field that you want to model it available in the boundary is considered, and you can consider it in your model. But for the number, for sure, the higher the better, because it's a machine learning technique, and machine learning technique based on data. So if you have less data, you will have high uncertainty. If you have more data, you will have more certainty. And of course, it depends also on your secondary variable will give you a better result. So the secondary variable will reduce the uncertainty for you. The secondary variable, I mean, the data coming from seismic. So Hadi, if this is answered your question, as I said, higher number, the better. Is there any difference between exporting a static model built in Petrel to Eclipse Reservoir simulation for them and run the model in Petrel using for this one? I think this one need to be asked for the reservoir sessions. I cannot answer this one. Okay, this one you can ask it for the reservoir engineer. I think we have a session dedicated for reservoir engineer, for reservoir simulation. Yes.
So Abdurrahman, we have earlier a question from Ornaldo. He said, why use stochastic methods if we can apply deterministic and have a standard result?
This is a good question. Deterministic, you will have one realization. Let me show this slide. Okay, I got here. This is just for illustration example. It's not. This is not like what's happening in the algorithm of the software. So in deterministic, imagine this is the well 1. This is well 2. When I do all the virogram and interpolation method, I will get this blue line, which is one realization. But does this represent the truth? Does this represent the truth? The answer is not. We are not certain. We are not certain. We don't know if this is the truth in the middle, because we have, for example, if you have in the middle, let's say in the middle you have a value of acoustic impedance 700. Where is the acoustic impedance? Let's go. Let me show you data available in this data analysis. Maybe we have 700. If we have 700, it could be shale, it could be sand, it could be levee. So all this is different realizations. Okay. So what the software will do, we'll make a random selection between these realizations. We'll convert it to a probability distribution curve, and then we'll select randomly between them. For example, here, if we have 13,000, if the software select random point here, we will have high probability it is shale, but low probability it is levee. But here we have low probability shale, maybe sand, maybe levee, maybe another one channel. Okay. So because of these different probabilities, we need to have different realizations. So the stochastic will give you one map, maybe shale, the other map maybe at this point between these two wells. And then you will measure uncertainty. Because there is no, we cannot measure reality directly. We need to take it as uncertainty. Okay. Does this answer your question? And the stochastic is the standard way. Deterministic is just a basic, maybe to see QC, maybe use it as a smoothing to make a trend. Maybe I use it to make a trend because it's smooth. But stochastic is the standard, because we're taking into account all the change in the probabilities between the species. Yeah. Yeah, thank you. Any other questions?
Sorry, Abdurrahman, could you have WhatsApp in your number?
Yes.
Thank you.
Yeah.
So I believe there are no more questions. Thank you so much, Mr. Abdurrahman, for the
I hope it was I hope it was helpful session for you. You learned something new. Maybe in the future opportunities you will choose another topics. No problem. We will illustrate more about machine learning, about trend. We will find opportunities
would
in
be
the future.
great. That would be great. If we are open for any recommendation or any presentation you would like to present in the future.
Yeah. Okay, no problem.
Thank you so much.
Thank you, everyone. Thank you for attending and listening. Thanks for the question.
Have a great night.
Yeah, good night.